Picture this. A young Albert Einstein, barely old enough to shave, daydreaming about riding a beam of light. His mind was already wandering through the vast expanses of the cosmos, questioning the very nature of reality. Fast forward a few years, and that same daydreamer revolutionizes our understanding of the universe. He didn't just follow the path laid out by others. He carved his own, challenging the established norms of science. Einstein wasn't your typical scientist. He was a rebel, a thinker who dared to question everything. His curiosity knew no bounds, and his willingness to defy conventional wisdom set him apart from his peers. His general theory of relativity, a masterpiece of human thought, is one of the most profound ideas ever conceived. It wasn't just a scientific breakthrough, it was a paradigm shift that changed how we perceive the universe. It reshaped our view of gravity, time, and the very fabric of reality. Einstein's equations showed that space and time are intertwined, forming a four-dimensional fabric that can be bent and stretched by mass and energy. Forget apples falling from trees. Einstein saw gravity as the curvature of space-time itself. This revolutionary idea explained phenomena that Newtonian physics couldn't, like the bending of light around massive objects. Einstein's genius lay in his ability to explain complex ideas with elegant simplicity. He had a unique talent for visualizing abstract concepts and making them accessible to others. He used thought experiments, like imagining himself chasing after a beam of light, to explore the universe's deepest secrets. These mental exercises allowed him to break free from the constraints of traditional experimentation. His work wasn't just about equations, it was about pushing the boundaries of human imagination and daring to see the cosmos in a whole new light. Einstein's legacy is a testament to the power of curiosity and the relentless pursuit of knowledge. Forget everything you thought you knew about gravity. It's not about some mysterious force pulling things together. Einstein's general relativity says it's all about curves. Imagine a bowling ball placed on a trampoline. The ball creates a dip, a curvature in the trampoline's surface. That's gravity. Massive objects like stars and planets warp the fabric of space-time around them, just like the bowling ball on the trampoline. And just like smaller objects rolling around the dip, planets orbit stars because they're following the curves in space-time created by the star's mass. The Earth isn't being pulled towards the Sun. It's simply following the curves in the cosmic fabric created by the Sun's massive presence. It's a mind-bending concept. But once you grasp it, gravity becomes a whole lot more elegant and a lot less mysterious. Imagine yourself in an elevator, floating weightlessly. Are you in deep space, far from any gravitational pull, or are you in free fall, plummeting back to Earth? Here's the kicker. You can't tell the difference. This is the essence of Einstein's equivalence principle, a cornerstone of general relativity. It states that the effects of gravity are indistinguishable from the effects of acceleration. When you're in free fall, you're essentially weightless, just like you would be in the vast emptiness of space. Think about astronauts orbiting Earth. They're not floating because there's no gravity in space. In fact, Earth's gravitational pull is still quite strong up there. They're floating because they're in a constant state of free fall, just like that elevator plummeting to the ground. It's a thrilling counterintuitive idea that helps us understand the interplay between gravity and acceleration. Imagine drawing a straight line on a piece of paper. Now crumple the paper into a ball. The line is no longer straight, but follows the curves of the crumpled paper. That's a geodesic, the shortest path between 2 points on a curved surface. In Einstein's universe, objects don't move in straight lines through space. They follow geodesics, paths determined by the curvature of space-time itself. Planets orbiting stars, light bending around massive galaxies. These are all examples of objects following their designated cosmic lanes. Think of it like driving a car. You might think you're traveling in a straight line, but you're actually following the curves of the Earth's surface. Similarly, objects in space are always following the curves of space-time, even when it appears they're moving in a straight line. It's a cosmic dance, choreographed by the curvature of the universe itself. Black hole math. Unraveling the Schwarzschild metric. Black holes, those enigmatic cosmic monsters that gobble up everything that gets too close. They are regions in space where gravity is so strong that nothing, not even light, can escape their grasp. But how do we even begin to understand these bizarre objects? What tools do we have to decode their mysteries? Enter the Schwarzschild metric, a mathematical tool that describes the extreme gravitational field around a black hole. This metric, derived from Einstein's field equations, provides a solution for the space-time geometry surrounding a non-rotating, spherically symmetric mass. Don't let the math scare you. The basic idea is simple. The Schwarzschild metric essentially tells us how space-time is curved by the presence of mass. The Schwarzschild metric tells us how much space-time is warped at any given point around a black hole. This warping affects the paths that objects take when they move through this region. It helps us calculate the escape velocity, the speed needed to break free from the black hole's gravitational clutches. This is crucial for understanding the dynamics of objects near a black hole. Think of it like a cosmic drain, with the black hole at the center. Just as water spirals down a drain, matter and light spiral into a black hole. The closer you get to the drain, the stronger the pull and the harder it is to escape. This increasing gravitational pull is what makes black holes so fascinating and terrifying. The Schwarzschild metric helps us map out the contours of this cosmic drain, giving us a glimpse into the bizarre physics at play near these gravitational behemoths. It allows scientists to predict how objects will behave in the intense gravitational field of a black hole, providing invaluable insights into the nature of our universe. Time warps. When gravity messes with clocks. Time, it's the one constant in the universe, right? Not so fast. Einstein's General Relativity tells us that gravity doesn't just warp space, it warps time too. The stronger the gravity, the slower time flows. It's called gravitational time dilation. Imagine two identical clocks, one on Earth's surface and one in orbit, far from any gravitational influence. The clock in orbit will tick slightly faster than the one on Earth. It's not a mechanical malfunction. It's a fundamental consequence of the way gravity affects time. This mind-bending phenomenon has real-world implications. GPS satellites, for example, have to account for gravitational time dilation to function accurately. It's a testament to Einstein's genius that his theory predicted this bizarre effect decades before we had the technology to test it. The Fabric of Reality, a glimpse at the metric tensor. We've talked about warped spacetime, but what exactly is this fabric that's being warped? That's where the metric tensor comes in. It's a mathematical object that describes the geometry of spacetime. Think of it like a cosmic ruler, measuring distances and angles in the warped landscape of Einstein's universe. In everyday life, we use simple rulers to measure things. But in the realm of general relativity, we need a more sophisticated tool, the metric tensor, to navigate the curves and warps of spacetime. It's a complex concept, but the key takeaway is this. The metric tensor is our guide to understanding the geometry of the universe. It's the mathematical language we use to describe how gravity shapes the fabric of reality itself. Einstein's legacy, a universe transformed. Einstein's general theory of relativity wasn't just a scientific breakthrough, it was a revolution in thought, a paradigm shift that altered the very fabric of our understanding. It transformed our understanding of gravity, time, and the universe itself, revealing the intricate dance of celestial bodies and the unseen forces that govern them. From the bending of starlight to the expansion of the universe, Einstein's ideas have been confirmed time and time again, standing the test of rigorous scientific scrutiny. His legacy extends beyond the realm of science, permeating culture, philosophy, and even art. Einstein's name has become synonymous with genius, creativity, and the power of human imagination. His theories have inspired countless innovations and have become a cornerstone of modern physics. His work continues to inspire scientists, artists, and thinkers of all stripes, urging us to push the boundaries of knowledge and to never stop questioning the universe around us. The ripple effects of his genius are felt in every corner of intellectual pursuit. Einstein's universe is a strange and wonderful place, full of black holes, time warps, and cosmic curves. It's a realm where the impossible becomes possible and the unimaginable becomes reality. It's a universe that challenges our intuition at every turn, but it's also a universe that fills us with awe and wonder. Each discovery opens new doors to understanding, inviting us to explore further. And it's all thanks to the genius of a man who dared to dream of riding a beam of light, forever changing the way we see the cosmos and our place within it.